this slide here is good. Of course, my colleagues, Mr. Casanova, Dr. Wiedenfield, did a lot of this. So we'll touch on it some more. Very, very important stuff here in Chapter 3. Molar mass is very important. Avogadro's number. Did either one of those do percent composition calculations? You know, like if you had something like, let's say we had sodium phosphate. Yeah. Okay. I mean, we can redo some of these things. Yeah, let's do sodium phosphate, and then empirical formula is where you are given a percent composition and then asked to figure out what that would be. Molarity is a solution concentration, and then other solution concentrations, well, there's a whole bunch of them. There's parts per million, there's parts per billion, but the other one is percent, weight, volume, percent. You can say it as weight, volume, percent, concentration, or it will say mass, volume, percent. Those are the same thing. Molarity is really important because that's what chemists typically use. Weight, volume, percent is important because that's what you'll see in clinical environments, in drug concentrations. They're 0.2% solution. What is that? 0.2 weight, volume, percent solution of that drug. They don't go by molarity. Saline solution is 0.9% saline. So those are the two most important concentration terms to be familiar with and how to use. All right, so let's see, where does percent composition come in? Okay, molar mass, you good with that? Molar mass? Ammonium phosphate. Let's look at that one. All right, to do a molar mass, we're just going to fly through some of this stuff. But you got to figure out how many elements you have here. How many? So you got nitrogen, hydrogen, phosphorus, and oxygen. How many nitrogens? 3. How many hydrogens?
12.
Phosphorus? Oxygen? Okay. And so now to get your molar mass, you're getting these numbers off the periodic table. Those are the average atomic mass of these elements. So what would that be? 30, 42, what is that? 42.03. This is 64. Okay, so you just find all of those, add them up, and you get to the molar mass. All right? All right, so you see why getting the right chemical formula is essential to getting the correct molar mass. And what is the molar mass telling you? That's the number of grams that would be 1 mole of that substance. That's how much 1 mole of ammonium phosphate would, 1 mole of ammonium phosphate would weigh. That many grams. That would give you 1 mole of ammonium phosphate is giving you 3 moles of nitrogen, 12 moles of hydrogen, 1 mole of phosphorus, and 4 moles of oxygen. But that's what's in 1 mole of ammonium phosphate. And molar mass is going to be really critical. Okay, then there's converting grams to moles and moles to grams. I'm just going to flash down through some of these slides. Atomic mass is in AMUs. Molar mass is in grams. So the atomic mass of hydrogen is 1.008 atomic mass units. The molar mass of hydrogen atoms is 1.008 grams of hydrogen. But the molar mass of elemental hydrogen, there's 2 hydrogens, 2.016 or 2.02 grams equals 1 mole of hydrogen, elemental hydrogen. Because it is diatomic, you have to keep in mind the molecule has 2 hydrogens in it. An atomic mass unit is defined as 1/12 of the mass of a carbon 12 atom. So you take a carbon 12 atom, that isotope of carbon, and so the atomic mass unit is kind of defined around carbon 12. It's essentially the mass of a hydrogen atom, but it is exactly the mass of 1/12 of a carbon 12 isotope. Yeah, you can go in there and see the isotopes of all the elements. All right, I think why is that slide blank? I guess I left that blank to develop that. How you get those average atomic masses. These will appear on the quiz. Here's another one. Copper. Did one of the instructors do this one for you? Okay, good. All right, so you're basically converting this percent into a decimal. What is a percent? 69.09 per 100. That's what percent is. Per cent, per 100. You get an 83 on an exam, you got 83 per 100. You got 83 out of 100. So you divide your 83%, it converts into that decimal, 0.83. So all we're doing is taking away that percent sign, converting that into a decimal, multiplying it by that, and getting a number. We're going to do the same thing over here. Multiply it by that and get a number, and add those two numbers together, and you get the average atomic mass of copper, which should come out something like 63.55. Because copper is not, it's not atoms with a mass number 63.55. It's these isotopes. It's these isotopes that have this mass, but there's that relative abundance. Okay, I'm just having fun here, reviewing. So there you get your periodic table with the different atomic masses based on the isotopes. All right, this is going to come right off the periodic table. Is that right? Is what?
Molecular weight the same as atomic mass? Is that what he's still breaking?
Well, molecular weight would be like this. This is a molecule. And it would be 18.02 atomic mass units. That would be the weight of one of these molecules. The molar mass would be that. Okay? So that's, it's a little, it is a little confusing. I know when I learned this, we talked about molecular weight in terms of grams per mole. But I think the textbooks are getting a little detailed, and they're saying, okay, when I talk about molecular weight, I'm talking about the weight of a molecule. When I talk about molar mass, I'm talking about the mass in grams of 1 mole. That's what I mean by molar mass. All right, we got into Avogadro's number. There's a mole of each of those things. It's not a lot. You know, a mole of copper would be 63.55 grams of copper. That's about it right there. A mole of mercury, pretty heavy, 200 grams, 200.59 grams. Doesn't look like a lot of mercury there, but it's so dense that you can pack 200 grams in a little bit of volume. There's the amount, there's 12 grams of carbon. 12.01 grams of carbon. You got a mole. There's about 55.85 grams of iron, or of steel nails. And you got a mole of nails. All right, here's converting moles into grams. We've got 0.356 moles of zinc. We want grams of zinc. So I'm going to put moles down here. I need to know grams per mole, molar mass. Zinc. 65.38 grams per mole. And I convert that into grams. Okay, your given unit is moles, your desired unit is grams. You're going to divide by desired over given. Let's do that calculation and just think this whole thing through. If you want to do the very last step, and I mean these are simple and straightforward, but let's not ignore nice practical little things to do, like 0.356 times 65.38 is 23.3. Okay, now what you should generally do is look at this number, 23.3. It is less than 65. We're talking about less than 1 mole. This is what 1 mole weighs. So the answer should be less than 65. Okay? That's what I'm just doing right here. You're not a robot that just transfers numbers from a calculator to a piece of paper and generates an answer. You're a human being that checks to see if things seem reasonable. If your answer comes out to be 233 grams of zinc, you should say, that doesn't look reasonable. If one of them weighs 65 and I got less than 1, then it should be less than 65. Okay? Follow me? So do that. Don't skip over that step. Is it reasonable? You go into a gas station and get gas and buy candy bar or whatever and give them a $20 bill. You're not happy if they give you $1.50 back. You do a reasonableness. You might not count the change down to the penny. You might, but you might not. But they better give you about $19 back or $18.50 or something. Depends on how expensive the candy bar was. But you do that with your money, you might as well do that with your chemical calculations. Okay, how many atoms are in 60? Did they do all of these? Am I redoing a lot of stuff? Okay, let's just keep moving then.
He was upset that there weren't answers. He would do it. He's like, how come you didn't put the answer?
It did what?
He would do the problem and he's like, and where's the answer? How come he doesn't put the answer? So we haven't answered any of the questions.
Yeah, so we weren't sure if the answer was right.
Okay, well, let's just do it real quickly. What is this? How many atoms are in 16.3 grams? Well, let me erase this for a second. Okay, look at that question. How many atoms are in, plan out a strategy when you're solving a problem. Plan out a strategy. I'm given grams. They want to know number of atoms. Well, right away I can see that I need to convert my grams into moles. Because I know what a mole is. A mole is this many things. Doesn't matter what I'm talking about. That's what a mole is. So if I go from grams to moles, then I can multiply my moles by that many things per mole. And I can convert the moles into the number of things. All right? So I'm looking at a strategy here. I don't have a conversion factor that'll take me from grams to atoms. I have to go through moles. Because everything on there, a mole of it has a different weight. Sodium is 23 grams of sodium per mole. Iron is 55.85 grams per mole. So I can't just go from grams and say that's going to be this many atoms. I got to say, what are we talking about? Now we're talking about sulfur. What are we talking about? 16.3 grams of sulfur. So I'm going to take my 16.3 grams of sulfur and I'm going to convert that into moles of sulfur. How do I do that? Well, I put the grams of sulfur down here. 1 mole of sulfur weighs 32.06. Is that what you have on your periodic table? 0.7? Okay. 32.07 grams of sulfur. And at that point now, what do I have? I have moles of sulfur. Then I know that there are 6.022 times 10 to the 23rd atoms of sulfur per mole of sulfur. And now I have atoms of sulfur. Okay? So there you can see my strategy above there. I'm going from grams to moles to atoms. I have to go through moles. So let's do that calculation, see what that answer is. 16.3 divided by 32.07. Times, and what I'm going to do when I times this on my calculator, I'm gonna put this in parentheses. I'm gonna use my scientific notation thing, times, I'm gonna put parentheses around that. It won't, I don't think it would make a whole lot of difference on this problem. So I'm getting .06. All right, let's do a little bit of a reasonableness check on this thing. This number, I mean, you can see that this number is about half of that number, isn't it? It's still the same power, 10 to the 23rd, but that is about half of that. You kind of look at that, 16 grams of sulfur is about a half of a mole of sulfur. So that looks reasonable. If you come out with, 3.06 times 10 to the 42nd or something like that, then you'd say, whoa, what happened? This here is going to be a lot more important when it shows up in the denominator. When this is showing up in the denominator, I really recommend you bracket it, because otherwise sometimes what happens is the way you put it in there, it looks like you divided by this number and you multiplied by that number. You get the wrong answer. You see this 6.02 times 10 to the 23rd? If it's sitting down here in the denominator and you don't bracket it, it may divide this and look like it multiplied by that, and you do get a very different answer. Where's my marker? There we go. Okay, is that good? YouTube, I don't know what that is. We won't worry about it. You can go watch it. Okay, here's one where we just did this thing here. What is the composition of each of these compounds? Really, how many nitrogens, hydrogens, phosphorus, oxygen? We just did that. Very important to be able to tear these formulas apart to know how much of everything is there. The one you haven't seen is let's look at that copper sulfate. I don't think you've seen this. This is a hydrate. Copper sulfate, it has a dot there. This is copper sulfate pentahydrate. That's what this is called. This one up here is anhydrous copper sulfate. It has no water of hydration in the crystals of the copper sulfate. This one does have water trapped in the crystals, and it does have an implication for the molar mass of this. The molar mass of this one, copper, you've got one copper, you got one sulfur, and you have 4 oxygens. That's anhydrous copper sulfate. And if you figured out what a mole of that, how many grams of that would you need to give you a mole, you'd have it there. And I could go across the hall here and get you a bottle of each of these. Anhydrous copper sulfate is kind of a light blue, real pale blue color. Copper sulfate pentahydrate is a vibrant blue, like your t-shirt. That's about the color of the pentahydrate, and the anhydrous is the color of your hat. You guys are sitting right next to each other. All right? Kind of a little paler than your hat and as vibrant as your shirt. You get water around the copper ion and it turns bright blue. So what is the molar mass of copper sulfate pentahydrate? It's going to have 1 copper. It's going to have 1 sulfur. It's going to have 4 oxygens. And now it's going to have 5 waters. If you want to just take them together, 5 times, we kind of are should be getting used to the fact that water is about 18.02 grams per mole. This has 5 of them. If you add all that up, now you have the molar mass of copper sulfate pentahydrate. So if I had those 2 bottles and I took that many grams of the anhydrous, I'd have a mole of copper sulfate. If I took this many grams of the pentahydrate, I'd have a mole of copper sulfate. So I'm going to take them both and dump them into water. I've got to weigh out more of the pentahydrate to get a mole of copper sulfate because it's got all of this stuff in the crystals. That's water of hydration. Very, very common. There's lots of ionic compounds that are hydrates. They're not always 5. It could be monohydrate, dihydrate, 12 waters, whatever. All right, so, yeah, is it Nathan? What? DJ. You were asking molecular weight. So here's the slide that's kind of teasing that out. So the molecular weight is in atomic mass units. The molar mass is in grams. So it's kind of making that kind of a distinction. If you were in high school and took chemistry and, you know, they talked about molecular weight as grams per mole, I wouldn't criticize them at all. I mean, sometimes you can hear it both ways. So molecular mass is in atomic mass units. Molar mass is in grams. Okay, you know how to do this now. This one is a little bit more complicated. It's just a lot. You just gotta add them all up. 8 times carbon, 10 times hydrogen. Get the molar mass. There's a problem. Yeah, let's do that. Percent composition. I was taking, here's one, but let's do a new one here, sodium phosphate. So come on over here and list out what you've got in this compound. You've got 2 sodiums, 22.99. You've got 1 phosphorus, 30.97. I should have let me have the periodic table in front of me that you guys have. The reason I like this one, so you can see some of this goes out to 4 decimal places. This goes out to 2 decimal places. It typically has 3 or 4 significant figures, and that's good enough. Are there more accurate numbers for these? Yes. And if you were really doing really fine, like if you were at the National Bureau of Standards trying to make sure that the average mass on tin was correct, you'd use really accurate numbers for the masses of the isotopes. But 2 to 3 or 4 significant figures is plenty for us. Yeah, phosphorus is 30.97. Okay, so we need to get this number down here to begin with before we get a percent composition. So this I know is 30.97. This one I know is 64. What's the top one? 40 what? And what's the addition here? 140? 0.95. That's the molar mass. That's the mass of 1 mole of this stuff. So if we had a mole of sodium phosphate, it would weigh 140.95 grams. Well, what would be the percent nitrogen in there? Now this is nitrogen, phosphorus, and oxygen, just to keep track of it. Well, 45.98 grams of the 140.95 grams is nitrogen. Sodium, excuse me. I'm sorry. Right, sodium. All right? So your percent sodium is what? What is a percent? What part of the whole is it? The sodium represents 45.98 grams of that 140.95 grams. So I get something like 32.62%. Let's do all of them. All right, the phosphorus, what part is the phosphorus of the whole? So we're always dividing by the total mass of the sodium phosphate. We're putting in the numerator what part of it is phosphorus. And then finally the oxygen. The part that's oxygen is 64 grams of the whole 140.95 grams. Okay, so what should those three numbers add up to? What? Hopefully 100. What we're saying is the sodium phosphate is 100% made out of sodium, phosphorus, and oxygen. These are the only three elements in sodium phosphate. So if we have the percent sodium, the percent phosphorus, and the percent oxygen, these should add up to 100%. And that's one way you can check yourself, is add them all up. I mean, it might be off by 1/10 or 100th of a percent because of rounding, but, and I wouldn't worry too much about that. It might come out to be smack dab. It comes out smack dab 100, doesn't it? All right? So you can do the percent composition on any compound. Just get your total weight, the mass of that compound, and then go ahead and do this. All right, now on quiz 3, I'm going to pull a question right off of quiz 3. I don't know if you'll be lucky enough to get this question, but you might. Yeah, let me, all right, so there's percent composition. You know how to do that now. Now, one thing you can do is you can go from a percent composition to an empirical formula. We won't go backwards on this one. I'll just give you another problem. We're going to start with percent composition and have you try to figure out what the empirical formula would be. See if I can get a new slide in here. So here's the problem. Is this all showing up over there? Good, good. I'm not looking behind me. Determine the empirical formula that's an O for a compound with the following percent composition. It's made up of potassium, hydrogen, phosphorus, and oxygen. And I think I mentioned this on Tuesday. Someone might come in to a lab, an analytical lab. It has all kinds of capabilities. And I say, what is this? What is this? They got something in a jar, in a vial, whatever. What is this? And the lab says, I don't know. Well, can you find out? Can you figure out what it is? Well, we can start trying. So the first thing we're going to do is elemental analysis. We're going to find out what elements are in there. And then we're going to do a percent composition by element. What percent of each of these elements are in there? And so, thank you, Skype. Go away. Oh, jeez, oh man. Is someone trying to call me? Okay. So then they do all that. They find out it's made up of these four elements, and they find out that it's 28.7% potassium, 1.5% hydrogen, 22.8% phosphorus, and 47% oxygen. And then they say, well, let's see. Maybe we could figure out what the ratio of potassium, hydrogen, phosphorus, and oxygen is in this unknown compound from its percent composition. Have you done one of these problems? No? Yes? No? Maybe? All right, the strategy here is figure out a certain amount of this to start with, and the best amount to start with is assume you have 100 grams of this. So what would you have? You would have, in 100 grams, you would have 28.7 grams of phosphorus, potassium, potassium. And you'd have 1.5 grams of hydrogen, and you'd have 22.8 grams of phosphorus and 47.0 grams of oxygen. How does that help you? Well, you now know how to convert grams of something into moles, don't you? That's what we want to get in an empirical formula. What is the ratio of atoms of these four elements in this compound? So we can't do a gram ratio, but if we convert these grams to moles, we're now getting it down to a number ratio, a discrete number of atoms. So we're going to convert this into moles. Go ahead and do that. Go ahead. I'll quit talking. You convert each one of these into moles and start trying to figure out what the empirical formula would be. Like I said, this is potentially one of the Chapter 3 quiz questions. Let me just point out here, like for the hydrogen, hydrogen is diatomic, but we don't care about that right now. It's not going to be in this compound as a hydrogen molecule. It's going to be in there as hydrogen atoms. So I'm going to use 1 mole of hydrogen is 1.01 grams of hydrogen. Because what I want to know is how many hydrogen atoms would 1.5 grams of hydrogen be, okay? I don't want to know how many hydrogen molecules it would be. I want to know how many hydrogen atoms. And likewise for oxygen, I'm going to get down to the molar mass of an oxygen atom, because I want to know how many that is. All right?
Do we get a mass in this combination so that we can check it?
Well, the only thing this question is asking is this: what is its empirical formula? So that's going to be the answer. You wouldn't, yeah. So you get numbers like this. Did you get something like this? And this is the number of moles. 1.49. The phosphorus here is like 0.736, and this is 2.94 moles of oxygen. Now, for an empirical formula, we want a whole number ratio of things. So the strategy now, you got the mole, we've got 0.73 moles of potassium for every 1.49 moles of hydrogen, for every 0.736 moles of phosphorus, for every 2.94 moles of oxygen. Take the smallest number and divide all of these by that number. And this, what does that do? That converts that into the number 1. This roughly the number 2, the number 1, not exactly 1, but round it off to 1, 2.94 divided by 0.734 equals what? 4. Look at that, 4. So what do we have? We have K1, H2, P1, O4. Or KH2, PO4. Okay? So that's how you go from a percent composition to a empirical formula. Yes?
So just a quick question, on the grouping packet, the problem 19 is the same thing. Do we assume it's still 100 grams and the packet also usually be on that?
Yeah, that would be the strategy to go all the time from a percent composition. I mean, you could assume 450 grams. You could assume any amount you want, but you would have to take that 28.7% times the 450. All right? So by assuming 100 grams, you don't have to do a calculator. You just turn your percent into grams. That's the beauty of assuming 100. All right? Whether it's 100 grams or 7,000 tons, it's 28% potassium. And you would get the same answer. You would just do a whole lot more work. You'd sweat harder. All right? This is a simpler way to do it. Or less effort. All right? And that's a pretty good formula right there. This is a compound, H3PO4. There's phosphoric acid. Now, what have we done here? We've taken one hydrogen away and replaced it with a phosphorus. So we have phosphorus dihydrogen phosphate. And that's the ratio of these elements to it. And if you get a number like 4.04, just round it off to 4. You know, in any laboratory doing elemental analysis, they're going to have a little bit of experimental error in there, so their numbers aren't going to just nail it down to a integer necessarily all the time. But if it's close enough there, that's a 1 to 2 to 1 to 4 ratio. Okay. Okay, this we've already gone over. You could calculate the percent composition of hydrogen, phosphorus, oxygen, and phosphoric acid. Okay, there is one more. You were asking the question. What's your name again?
Sarah.
Sarah? Sarah, you were saying, well, would we be given a molar mass so that we could figure out whether we're right? We don't know. But you could go from an empirical formula to a molecular formula if you're given a molecular weight. Have you done one of those? Yes? Have you done this one? Okay. You get the empirical formula and you would decide what does that weigh? What would be the molar mass of that if that was the molecular formula? And if it's doesn't agree with the molecular weight, let's see. Oh, okay, here's the molar mass is between 90 and 95 grams. If your empirical formula is 45 grams and your molar mass is 90 grams, you know, whatever this is, nitrogen and oxygen, I'm just fishing here, but if that weighed 45 grams, the molar mass is 90 grams, then you got to multiply this by 2. This is going to be N2O4. The molecular formula is going to be double your empirical formula, because you can see that your mass of your empirical formula does not agree with your molar mass. It's only half of it. So the empirical formula is really only half of really what the real molecule looks like. And when you multiply it by 2, you got to multiply each coefficient by 2. It's going to be in the same ratio, 1 to 2, 1 nitrogen to 2 oxygens, but there are 2 nitrogens and 4 oxygens. Like I say, I don't know if that's the answer to this question, but that's the thinking. Okay? So an empirical is just the lowest integer ratio of the elements in that compound. The molecular formula is the actual ratio of elements in that molecule. The actual. Hydrogen peroxide, that's its molecular formula. Its empirical formula is that. But that's not a molecule of hydrogen peroxide. That is. That's a molecule of hydrogen peroxide. Empirical. Molecular. Okay, let's take a break. Let's take a 5-minute break, and then I think maybe we're ready to review concentrations. Okay, molarity and percent, weight volume percent.
Give an example of the molecular formula or just empirical?
We just talked through one. We didn't really do it in detail. Yeah, so if you're ever asked for the molecular formula, if you're ever asked for the molecular formula on one of these percent composition problems, you have to be given a molar mass. Okay? If you're not given a molar mass, you can't determine what the molecular formula would be. And you have to compare your empirical formula mass to your molecular mass to get there. Maybe Tuesday, maybe we'll do that. But let's segue on into these and grapple with that. Look at an example. What are all these? So where is molarity? it in this chapter?
It's at the end.
Oh, I'm getting, it's at the end?
Read it out.
Okay, yeah, here we go. Oh, by the way, did anybody leave a charger here last Tuesday? For an iPhone? Here. Does it look like this? I didn't turn it in lost and found. I did assume it was someone in this class. I just thought I'll bring it. Yeah, that got brighter. Now I turned it. Okay, molarity. Molarity is a really important one. Moles per liter. There are other ways of doing concentrations, but molarity is the important one for chemists. All right, molarity. Yeah, we're back running here. Moles per liter. Now, you probably saw this on the slides in the other lectures, but just so you see it up close and personal. This is a volumetric flask. And flasks like this are used to make molar concentrations of things. Because keep in mind, what is 1 molar solution? It's 1 mole of that substance in a liter of solution. Okay, we're not talking about a mole of it in a liter of water. We don't take a mole of the substance and add a liter of water to it. To make a 1 molar sodium chloride solution, we would look at our sodium chloride and say, okay, I've got sodium, I've got chlorine, what am I doing here? So it's 58, so 1 mole is 58.44 grams of sodium chloride. So there's 58.44 grams of sodium chloride. To make a 1 molar sodium chloride solution, I would dump that in here, and then I would add water until it reached a volume of 1 liter. How much water would that be? Well, I don't know, and I don't care. How much space is the sodium chloride going to take up? It's probably going to take up some space, so I'm probably not going to get a liter of water in here, but I am going to have a liter of solution. That's what I want. I want to know that if I had 1 liter of this solution, I would have 1 mole of sodium chloride. Follow me? I don't care how much water. I just want to know if at a certain volume, 1 liter of this solution is going to deliver to me 1 mole of sodium chloride. So that's how you make these. If you go into a lab, and in our lab too, we have 1 liter 1 liter volumetrics, 500, 250s, 200, 100. And 10. There's a 10 milliliter volumetric flask. All right? What if I don't want a liter of it? I'm gonna throw the other 999 milliliters away. Doesn't matter so much when we're talking about table salt, but if I'm at a pharmaceutical company and the compound I'm working with is $2,000 a gram, all of a sudden I don't want to throw 995 milliliters of it away, throwing away thousands of dollars of stuff. I just need a little bit, tiny little bit. Pharmaceutical company will probably even have 1 liter volumetric flasks. All right, so this 10 milliliters divided by 1,000 is what? It's 1/100th. So there's 100 of these in there. So if I took my 58.44 grams sodium chloride and divided it by 100, I would have 0.5844 grams of sodium chloride. And if I took my 1,000 milliliter volumetric flask, divided it by 100, and milliliters, or which is 0.001 liters, that's 1/100th of a mole. Remember, that was 1 mole, so I have 0.010 moles of sodium chloride in 0.010 liters of solution is 1 molar sodium chloride. So if I were to take this, which is 100th of that, 0.5844 grams, and put it in this flask, which is 100th of the volume of that flask, I would have 1 molar sodium chloride. And I'm just doing that to prove the point that when you see this, it doesn't tell you how much of it you have. It tells you if you had a liter, you would have a mole. Okay? It's 1 mole per liter. I just happen to only have a 100th of a liter of it. But it is that concentration. The sodium and chloride ions would be floating around in a little flask at the same concentration, same abundance per volume as they'd be floating around in the big one. Okay, so that's molarity. And that's the beauty of molarity. You can take a certain volume of this solution and figure out how many moles of the substance you have. That is the beauty of molar concentrations. Because remember, compounds react with one another not on the basis of grams, but on the basis of atoms and ions and molecules, the numbers of them. They don't care what the other one weighs. They react in whole number ratios. Okay, so that's what you're looking at right there. This is the volumetric flask. It has only one marking on it. There's this it's scored in there. They've actually scored the glass. They don't put a mark on it. They score the glass at the 1 liter level. And that's all this flask is good for, is making various molar concentrations. If I put a 0.5 mole of sodium chloride in there and fill it up, I'd have a 0.5 molar sodium chloride solution. All right, how far did you go with these? Did you do all these calculations? Okay, let's just, we'll buzz through a couple of them. Calculate the molarity of a 150 milliliter solution containing 0.250 moles of sodium hydroxide. So what we have here is but remember, always go back to your defining equation. Molarity equals moles per liter. So take your moles and put it in the numerator. It's per liter. So we're going to want to take our 150 milliliters and convert it into liters. If I divide 150 by 1,000, it's going to be the same as moving that decimal place over. Three places. All right, so just keep that in mind. You have any number of milliliters. You can convert that to liters by it's dividing by 1,000 or moving the decimal place 3 places to the left. Converts milliliters to liters. That's beautiful. So now we've got moles per liter. So just do the calculation. And you'll convert that into molarity. Now, I like to see the answer like that. Not just 1.67 molar, but molar what? Sodium hydroxide. If we went over into the lab, we would not label a bottle 1.67 molar. If I went into the lab and saw a bottle like that, I'd say throw that away. We don't know what it is. We know what concentration it is of whatever it is, but we don't know what it is. All right? So we could have 10 bottles in there that are 1.67 molar, sodium hydroxide, hydrochloric acid, sodium chloride, whatever. Okay, so the complete answer is not only the concentration, but what is the solute that's in that thing. That it needs to be properly labeled with its concentration and its identity, what it is. So, what do we got here? That answer. All right, so just always hearken back to the definition of molarity. It's moles of solute per liter of solution. Okay. Now here's a very similar problem. We're going to start out with that definition up there, moles of solute per liter solution. We already know the denominator is 0.150 liters. Numerator, we've got 10 grams of sodium hydroxide, and we're going to need to convert that into moles. Sodium, oxygen, hydrogen. It's 1 mole of sodium hydroxide is 40.00 grams sodium hydroxide. So what I've got there, 10 divided by 40 is 1/4 of a mole per 0.150 liters. And boy, that gets us right back to where we were in the previous problem, doesn't it? Do that calculation. Okay, so what these slides are doing, they're just bringing to you various kinds of problems that you would face. Any question about that?
I missed what you did. What did you convert them to?
I'm converting the grams of sodium hydroxide into moles. And how am I doing that? Here is the molar mass. Okay? So 10 grams of sodium hydroxide multiplied by 1 mole per 40 grams. I'm dividing the 10 by 40 to convert my grams of sodium hydroxide into moles of sodium hydroxide. Why am I doing that? Because that's the way molarity is defined. It's not grams per liter, it's moles per liter. So down here I'm given the grams of sodium hydroxide, and I can convert that into moles.
Mr. Rio?
Yeah.
So, top part with the conversion, like this milligrams to grams, do you have to do any extra steps versus?
If it's milligrams, I'd convert it into grams, because your molar masses are not in milligrams, they're in grams. Yeah, so if it's milligrams, it's going to be a very low concentration, unless it's a lot of milligrams.
Yeah, because one of the questions had milligrams as well.
Okay, yeah, I'd convert the milligrams into grams, and then convert the grams into moles. And yeah, all right, so it's always this is the definition, moles per liter. You're given a volume other than liters, you got to convert it into liters. Usually you are given milliliters, because that's 9 times out of 10 what the stuff in the laboratory. Even this 1 liter volumetric flask is labeled 1,000 milliliters. All right? So milliliter is the most common volume unit in a laboratory piece of equipment. A burette, a graduated cylinder. Even this thing, they don't just say 1 liter, it's 1,000 milliliters. But 1,000 milliliters divided by 1,000 is 1 liter. All right, now this question here, before we answer this question, this is a very practical question. There's people working over there right now making solutions. I just went in there to get this bottle, and one of the lab techs said, should I pour this in? You know, he's over there making a solution. He said, I think this is for one of your labs. So they're making solutions. Let's say you know you want 200 milliliters of a sodium chloride solution that is that concentration. Or let's say I know that's what I want, and you work for me. And I say, go make that. You got to figure out, how am I going to make that? Well, you're going to have to weigh out so many grams of sodium chloride. How are you going to figure that out? Well, let me give you this is our molarity is moles per liter. Now, if I were to take moles per liter and multiply it by liters, let's just do dimensional analysis. What would I get if I took moles per liter times liters? What would be the unit? Mole. Right? Liter would cross out with liter, and that would give me moles. All right, so how does that factor into this problem? There's molarity, 0.125 molar sodium chloride solution. We want 200 milliliters of it. So let's take our 0.125 0.25 molar. Now remember, when I see a capital M there, what you should be seeing is moles per liter. Okay? I'm going to multiply that by 200 milliliters is how many liters? So molarity, so what we really have here is molarity times volume in liters equals moles. And that's exactly what I have done here. I have molarity times volume in liters, and that's going to give me moles of sodium chloride. What is that? And we probably have enough latitude here to throw another 0 on there. This is 3 significant figures, 4. So 0.0250 moles of sodium chloride. Well, does that answer this question yet? No. But does it get us close to the answer? Yes. Because now you are proficient at converting moles to grams. All right? So this is not the answer, but boy, it is on the way to it. Now I know how many moles of sodium chloride I need to weigh out. So I need to weigh out that many moles of sodium chloride. Oh, let's see here. I need moles. I need my units here. Moles of sodium chloride times 1, or it's 58. We got it right on the board, I think. 58.44 grams of sodium chloride per mole. Sodium chloride. Boink, boink. And now, does that give me my answer? Yes. How many grams? .46. Okay, now, I told you this is a practical problem if you were in a lab and wanted to make this solution. So what would this person do? Now they're armed with that. They know they need 1.46 grams of sodium chloride. I have indicated I wanted 200 milliliters of this. So they're going to go find a 200 milliliter volumetric flask. And what are they going to do? They're going to weigh out 1.46 grams of sodium chloride and dump it in the bottom of this flask. Probably rinse out what they weighed it in so that they know they got every little bit of that in there, and then they're going to fill it right up to there with water, and they would have a 0.125 molar NaCl solution, 200 milliliters of it. Okay? So that is a standard laboratory problem. Anytime you want to make a particular solution, you have to figure out how much of the solute to start out with. And that's how you do it. You usually know how much you want and what concentration you want. So then you have to calculate the mass that's needed to make it. Follow me? All right, so that's a real typical problem, and keep this in mind, that molarity times the volume in liters equals moles. Why does that have to be in liters? Because that's moles per liter. You got to multiply it by liters. Can't multiply it by milliliters. Got to multiply it by liters to get it to moles. Okay, this is essentially the same exact question, just worded a little bit differently. The other one is you're going to make that solution. Here you got the solution. You just kind of want to know what's the mass of glucose that's in here? Same thing, moles times volume in liters is going to get you the molarity times volume in liters is going to get you moles of glucose. And then you'd have to multiply that by the molar mass of glucose, and you get grams of glucose. All right, so this is really the same thing. So then you take the moles times its molar mass, and you'd get grams. The molar mass is going to be grams of glucose per mole of glucose. I won't do that one, but that's how you do it.
Maybe over top 24, or it says maybe over in class.
24 what? In,
Packaging.
okay, I don't know if I've got a packet. Let me see what 24 is.
It's looking for one out of the.
Oh, we will do this one. Okay. All right, let's do that. Calculate the molarity of chloride ions present when 15 grams of calcium chloride. Okay, this is kind of like this problem right here, but it's not talking about, it's talking about the molarity of sodium nitrate. This one is taking it a step further and saying, what's the molarity of the chloride ions? So, I'll title this Chapter 3, Group Work, Question 24. Is that right? Oh, let's see. Calculate the molarity. I'm going to shorthand this a little bit. Chloride ions in a solution that has 15 grams of calcium chloride in 250 milliliters of solution. Yeah. Okay. Well, eventually we're going to need to know the molar mass of calcium chloride. I can see that coming. So let's figure that out right over here. Calcium 1 times chloride. And what's the total?
110.98.
Everybody agree? Or at least two other people? Okay, so its molar mass is 110.98 grams, calcium chloride is. So why do we need that? So calculate the molarity. Well, let's figure out what the molarity of our calcium chloride is first. We've got 15.0 grams of calcium chloride. Remember, molarity is moles per liter, so in the numerator we want moles, and in the denominator we want liters. Okay, that's going to be the molarity of the calcium chloride. Now, we could finish this off right here by simply putting in one more factor. There's more than one chloride in 1 mole of calcium chloride, isn't there? There's how many? 2. You can see that in the formula. It's CaCl2. So there are 2 chlorides for every 1 calcium chloride. Is that true? Is that right? That's the ratio of chloride ions to calcium chloride. So this will get us now the molarity of the chloride ions is going to be that right there. It's going to be double the molarity of the calcium chloride because there are 2 chloride ions in every CaCl2 formula. Is this right? All right, there are times when that is what you want to know. If you know that if you know something is got silver, that silver ions are going to react with chloride ions to form, for example, silver chloride. You want to know what you might have a solution of silver nitrate at a certain molar concentration. So you know the molar concentration of silver ions. You don't just want to know the concentration of the calcium chloride. You want to know what is the concentration of chloride ions in that solution, because they're going to react 1-on-1 with the silver to form silver chloride. All right, so you would want to react. You would want something like 1.08 molar silver nitrate reacting with this solution, which is really only like a 0.54 molar calcium chloride. This is that, but it's actually 0.54 molar calcium chloride, right? Because the calcium chloride delivers twice the amount of chloride as it does calcium chloride. All right, so there are times when you really do want to know what the molar concentration of the ions are floating around in there. Okay, dilution. Did they talk about dilution? You remember the formula. Okay, this is another practical problem in the laboratory. Because what happens in the laboratory is we order concentrated hydrochloric acid. And what is it? It's roughly, or it's about 12 molar hydrochloric acid. That's an N. Concentrated hydrochloric acid. So we get a bottle, maybe a 2-liter bottle of concentrated hydrochloric acid, and we make any solution of HCl we want from it. We can make 6 molar, we can make 3 molar, we can make 1 molar, we can make 0.5 molar, 0.1 molar. We can make all those HCl's. What are all those numbers? All those numbers are less than 12. We can't make 13 molar hydrochloric acid out of concentrated. How are we doing this? We're adding water. You go to HEB and you buy concentrated orange juice concentrate, frozen orange juice. And you bring it home. You don't have any orange juice at home. All you have is water at home. And so you defrost your orange juice, your orange concentrate, and you add, 6 cups of water, maybe 6 cups of water for every cup of concentrate, and you got orange juice. You're diluting it. So what this slide is trying to show you here is however many moles of the solute was in the concentrate, there isn't going to be any more of them in the dilution. There's more water. There's not more hydrochloric acid. Follow me? If you got a mole of hydrochloric acid here, and now you have doubled the volume, you've doubled the volume with water. You have 1 mole of hydrochloric acid here in double the volume. So what have you done? You've halved the concentration. If you double the volume, you're going to have the concentration. You're diluting it. So here's your dilution equation, where this is your original concentration. This is the amount of that concentrate is going to equal the new molarity times the new volume. Let me give you the theoretical basis for that. What I'm saying here is that the moles of the solute, let's say HCl, in this equals the moles of HCl in your final diluted solution. Not the molarity, the moles. You haven't added any more HCl to it. Well, what is the moles of HCl there? Well, the original concentration times the volume is moles. And what is this? The final concentration times the final volume is moles. The moles of HCl are going to be equal, so that stays equal. All right, this may still seem a little abstract until you look at it. So let's say we have 12 molar. We have 12 molar concentrated hydrochloric acid, and here's our practical problem. How many milliliters of concentrated HCl is needed to make 500 milliliters of 3 molar HCl solution? Here's our equation. Let's just take stock of what we know. This is 12 molar. What's V1? Unknown. That's what we want to know. What is M2? And what's V2? All right. So if V1 is what I want to know, I'm going to divide this by M1. And I'll have that V1 equals M2 V2 divided by M1. So I have my final molarity times my final volume divided by my original molarity, and that's V1. Molarity crosses out, my units are milliliters. So how many milliliters of concentrate do I need? Work your calculators. Get your money's worth out of your calculators. How many milliliters? Go ahead. So what would the lab technician do here? 125 milliliters, okay? So the lab technician would get themselves a 500 milliliter volumetric flask. They would get a graduated cylinder, about a 250 milliliter graduated cylinder, and they would get 125 milliliters of concentrated hydrochloric acid and pour it in here, and then they would add water, distilled water, right up here. This is violating a little bit of a lab rule. You should add acid to water and not water to acid. But yeah, if I were doing it, I'd put a little water in here first. I'd put a little water in here first, and obviously knowing that I don't want it to go over 500 milliliters. So I'd put some water in here, dump this 125 milliliters in there, and then finish it off with water. Right up to there. And I'd have 3 molar hydrochloric acid. Wear goggles, rubber gloves. Concentrated, you open the bottle of concentrated hydrochloric acid and HCl molecules, fumes are coming out of there. And boy, those will clear your sinuses. Okay, so that's how you do that. Now, some of you might look at this and say, well, isn't molarity times volume in liters? Anybody, that goes through anybody's mind?
So it stays in milliliters?
Yeah, if we converted them to liters, it would come out the same way. I mean, if we converted that to 0.50 liters, then we would end up with 0.125 liters. And if it says how many milliliters, we would multiply this by 1,000 milliliters per liter and get the same answer. All right, so you have to be careful when you leave it in milliliters. There are times when you, like on those other calculations where we're trying to figure out the grams, we got to convert it to liters. We got to know we're getting the moles. So you got to be careful.
Back, real quick back to concentration, when you're calculating the molarity and like these questions that have like milligrams and milliliters, should you change that to liters?
Let me see an example.
Concentration.
Which problem?
It's asking for the molarity, like this one right here. Like, this is that.
Yeah, I would change the 270 milligrams of sodium chloride to grams.
To grams, right, and then the 1 milliliter, do I change it to liter?
Yes.
Okay, so
Yes.
in that case-
And what helps you figure that out? What helps you figure that out, this is problem 23B. What helps you figure that out is this definition. moles per liter. So what has to go in here is moles, and what has to go in there is liters. So your milligrams need to be converted to grams, so you can convert that to moles, and your milliliters need to be converted to, if you had ounces, you'd have to convert it to liters.
But in dilution, they might ask you for milliliters, so.
Yeah, in dilution, you might be asked for milliliters here, and, yeah, you just, here you don't need to make that change. This really isn't giving you moles of HCl here, millimoles. You're getting kind of millimoles, but you're going to weigh out or measure out your HCl as milliliters. Okay, so that's what's going on here. Calculate molarity made by diluting. Well, maybe we won't do this one by diluting 25 milliliters of 6. Let's figure out. Now remember, the equation is M1 V1 equals M2 V2. So let's read this problem and decide what these numbers are. And it says calculate a molarity. What molarity are we calculating?
2.
Okay, we're calculating M2. So at this molarity right here, this is your M2. So what is 25 milliliters of 6 molar HCl? What are these parameters in this equation? So we now know this is our unknown. This is what they want us to calculate. 25 milliliters is what? V1. 6 molar HCl is what? M1. 500 milliliters is V2. All right? So you already know here that what you want to do, if you want to calculate M2, you're going to rearrange that equation like that. Calculate M2. So yeah, learn, and this is how I attack a word problem. I go in there and say, okay, what am I being asked to calculate, and what am I given? What are the numbers I'm given? And then what is the equation that would guide me through this problem? Okay, so take stock, and if you need to do something like this, don't. I should say M1 V1, M2 V2. I mean, if you have to make yourself a little list, make it. Nothing wrong with that. When I grade problems like this, a number of different problems like this, Boyle's law problems are like this. What's the most frequent mistake? They get V2 in the numerator and they get V1 in the denominator. The units still come out right. This is where unit analysis doesn't help you. The units still come out right, but you got the wrong parameter in the wrong place. V1 is 25 milliliters. So that has to be here. V2 is 500 milliliters. That has to be here. You get those switched, you get a whole different answer, right? So you have to carefully they're both volumes. So I need a volume in the numerator. Yes, you do need a volume, but you need a particular volume in the numerator and a particular volume in the denominator to get the right answer. Okay, we still didn't do weight volume percent. There it is. Weight volume percent. Calculate the percent weight volume of 200 milliliters. We only had one break today. You guys all right if we go for another 15 minutes and then call it quits? Is that good? Okay, let's do that. Let's just touch on weight volume percent. I don't know how many more slides are in. Oh, there's only a few more slides. Okay, so let's just touch on this so at least you got enough ammunition to wrestle with it. Like I said, this is the clinical situation. We'll do saline solution in just a second. Okay, this is grams per milliliter times 100%. Very different from molarity. Molarity is moles per liter. This is grams per milliliter. Calculate the weight volume percent of 200 milliliters of solution containing 20 grams of sodium chloride. So, plug numbers into that equation. All right, so this is the definition of weight volume percent. It's the weight of the solute per volume of the solution. Could almost do this in our heads, or so this is a 10% weight volume NaCl solution. Is that what it is? Yeah, sodium chloride. 10% sodium chloride. Saline, all right, in the hospital, they have these bags of saline. You can't give water in an IV. It has to be saline solution. You can drink a bottle of water, it won't hurt you. You put water, pure water, in your blood veins and it'll hurt you. Because of osmotic pressure, you will dilute out the plasma, the blood plasma, such that now the saline concentration outside the red blood cells is lower than inside the red blood cells, and it stresses the red blood cells. So you have to give saline solution, and it's 0.9% saline. So what that is saying, it's 0.9 weight volume percent. It's 0.9 grams of saline per 100 milliliters of solution. .9 per 100 milliliters times 100% is a 0.9% solution. And, okay, is everybody kind of on stream here? Why do they do this? Many drugs are very complicated formulas. You know, you go look at it and it's C27, H42, O19, S3, N44. Okay, it's got this huge formula. If we do know its molecular structure. Sometimes we don't. Sometimes it isn't a pure molecule. It's a mixture of molecules. So trying to get to a molecular weight and express a drug concentration in molarity ends up being a practical nightmare in a lot of cases. So they just say, okay, I'm going to take a half a gram of this and put it in 100 milliliters of water, and I'm going to have a 0.5 weight volume percent solution of this drug. Okay, so even coming up from the pharmacy in a hospital will be bags of drugs that are these kinds of concentrations. So many milligrams per liter, or grams per liter, or something like that. They're weight percent solutions of these drugs. Okay, now here's the harder calculation. Calculate the number of grams of glucose in 750 milliliters of a 15% glucose solution. So what do we have here? We have that 15% equals X number of grams of glucose per 750 milliliters times 100%. This gets to be, okay. So there's your unknown. It's saying calculate the number of grams of glucose. Here's the situation where you want to make 750 milliliters of a 15% glucose solution. How am I going to make it? Well, I got to calculate how many grams. So if you wanted to, let's simplify this a little bit. What we got here is 15% equals X over 750 times 100%. Okay? I'm just cleaning it up a little bit. So what do I have to do here? Let me clean this one up a little bit. 15. Well, if I divided this by 100%, I would have to divide this by 100%. And if I multiplied this by 750 milliliters, I would have to multiply this by 750 milliliters. And I'd solve for X. Okay? So just kind of clean it up a little bit and do the algebra to isolate the X. And let's calculate that, and we will just about be done here. And X equals what? Stick with me. I know we went through a lot of dry calculations today. I apologize. I'll try to get some new jokes or something. I don't know. All right, so what's X? $112.5 grams. Now let me make a suggestion right here, because this one you can kind of get confused on this one. Here's my suggestion. You got that answer. Now pretend you don't know. Pretend you don't know the percent, and plug this back into the equation. And see what you get. Double check your answer. And what do you get? 15%? That's what you should get. And that's how you double check your answer on this kind of calculation. All right, I think there's the solution to that one. there's a problem you could do. Okay, here's other concentrations. Part per thousand, PPT, parts per thousand. ppm, parts per million, 10 to the sixth. ppb, parts per billion. The THMs, some of you looking at the SAWS water report, I think they report these in parts per billion. They report calcium concentrations in parts per million. All right, so these are things that you'll see in the literature. And that's it. All right, so pass in chapter 2, group work. Hand in chapter 3 on Tuesday, excuse me. Work on those quizzes. Where's the sign-in sheet? Can we pass that around one more time? Did I ever send it out?
Sent it out at the beginning.
Okay, where did it go? Sign-in sheet. Yeah, can we just pass that sign-in sheet around one more time? And I wanted to see if these practice quizzes are in your class, in your Canvas. So I'm going to go to your Canvas right now, right here. I'm going to go to your Canvas course, and let's see what we find there. There's the Canvas course. I'm not sure these are here, but let's look. Let's look at quizzes. I hope they're here. Yeah, you got those quizzes. I'm not in the student view here, but yeah, here you go. I could go to student view. No, there they are. If you scroll on down in quizzes, these are practice quizzes. These are really helpful. You go in here and you say, okay, well, this is preview, but if you went in there, it would say, do you want to do the quiz? I'll just show you real quickly. Student view, quizzes, practice naming compounds. This is not for a grade. Okay, take the quiz. All right, I want to take the quiz. Go ahead and take the quiz. It's going to give you 20 questions. What is the name of the following ionic compound? Let me just do one real quickly. The way you do this, don't capitalize it. Lithium bromide. All right? Calcium bicarbonate. Don't capitalize it and put a space between lithium and bromide. I'm going to say I'm done, and I'm going to submit it. It's going to tell me, you left 19 of these questions unanswered. So I've got 1 out of 20. All right? So there's correct. I said, you didn't answer this. Incorrect. But that's correct. And if you did this quiz and get a 19 out of 20, then fine. Don't do it again. If you get a 10 out of 20, do it again, and it'll give you 20 new, it'll probably give you, randomly pull some new things. And then there's another one. Let me just do one more real quickly. Writing formulas, because you got to write these formulas a certain way. What is the correct formula of magnesium? Well, let's do calcium sulfide. No, let's do one that needs some numbers. Aluminum sulfate. The correct formula of aluminum sulfate is Al2 parentheses SO4 parentheses 3. I think that's right. Okay, but they're not subscripts. I can't figure out how to put the subscripts in, so don't worry about subscripts. Just put in regular numbers and say, okay, let's see if I got that right. Submit. Says you left 19 unanswered. Yes, I did. It's not, okay, there you go. Correct. AL2 parentheses SO4 parentheses 3. No spaces, no subscripts. All right? So you can do those practice quizzes as many times as you want to do them. All right? They won't grade them, but they will tell you, you got 18 out of 20 or you got 13 out of 20. Then you can do it again and again and again. All right? All right. I'll see you Tuesday.